let's move on to the, let's see how much time. Okay, 15 minutes. Hopefully this time I can get through it. So, now the second example is the diffusion equation. Another PDE that we'll cover later in another chapter. And but the form is slightly different. There's alpha squared here, and then the time derivative, I'm writing it in the reverse order. Just the same writing. Okay, partial, now you change the variable. It doesn't matter, partial psi, partial t is alpha squared, partial squared, partial x squared. So that's called the diffusion equation. Okay, now you do the same thing, but this time you have only one time derivative, so you only need one initial condition. And again, you are doing the Fourier transform in X only. And again, your textbook uses string variable for the wave number using Y. Wave number, I don't know. I don't know. Let's just use our convention. So you can write down the Fourier inverse Fourier transform and the Fourier transform pair. It's just like this, what we did before. Except that now the Fourier transform, let's call it capital psi, depending on the wave number. And then E, again, minus convention, x times k times x. That's the inverse transform. So the Fourier transform is this the same, except for changing the sign of this and this. Okay, and we want to do the initial condition. Initial condition is initial condition. I think your textbook has the initial condition. A little later, we'll talk about that. Let's solve the differential equation before talking about the initial conditions. Okay. Solving the differential equation. Now, using the same trick, this for the taking the Fourier transform, the whole thing, whole equation, that give you minus k squared capital psi as the function of k. This is the right hand side. It's ddt capital psi. Right? So that is even simpler than what we had before. This is the diffusion is just an exponential function evaluate at maybe the coefficient at 0, t equals 0, and the rest is just this. This is your like the decay rate, right? Minus right? Because you substitute this to this, you recover this. So obviously, because this is just an exponential function, right? Everyone see that? This is the solution of this differential equation. Okay, so that will actually give you a convenient way to specify the initial condition. So the initial condition is with the initial condition of what capital psi is this one, the coefficient in front of the solution, right? Obviously, and so this initial condition of the function itself is the substitute, whatever you have over here. Okay, and that that is fine. And then so that looks like a genuine solution. I mean, this is just a constant. This is just a constant, and this is the initial condition, and the full solution is just simply this. Everything is the same except you have the extra Gaussian, like a Gaussian in K, right? You still have that, and then you have a Gaussian, and then you have this ikx minus ikx factor integrate over K. So and obviously this is you can in principle just use the inverse Fourier transform and get whatever the using this to solve for that. It's just to be more specific. If you have an initial condition of in psi, then the capital psi at t equals 0 is given by this integral. Yeah, it's a Gaussian. Yeah, a Gaussian of a Gaussian is a Gaussian. You need to figure out the coefficient, and the coefficient depends on the convention also. But yeah, the generally is Gaussian. Okay, if you have so this gives you whatever is the initial condition of psi, you put in the Fourier transform integral and get the initial condition on capital psi, put it in here, then do the integral will give you the solution. All right, so that's the process, and that looks like a general formula. The rest is just a specific case. The specific case is that this, I think it's just say that this is, if this is a constant, if this is psi K0 is a constant. If this is a constant, then obviously you can figure out what the initial condition is psi, right? If this is a constant, what is this anyway? If this is a constant, call it C. I think your text will call it C. If this is a constant C. We just went through that. Yeah, delta function. Right. So for this C equals a constant, then the initial condition is just obviously you get 2 pi times C times delta X and 2 pi times, and then divided by of 2 pi, you get all together this what I get, right? This integral. Oh, there's a C. C. The C doesn't include in this way. Okay. And that is this one. So this is the initial condition. It looks like slightly more unphysical because yeah, delta function. Delta function is just an infinity for this one at x equals 0. It looks like unphysical, but this kind of spike or unphysical situation will get resolved by this alpha or at any finite t finite positive t because of the Gaussian. Make it regular again. You see that right away. This is C. This is a C. And this is C. And this go at 2 pi. Let this this t minus 1 dk. Right. And now you recognize this is like the inverse transform of a Gaussian with a k squared, right? And obviously you can just look that up and right, you can look that up. where did where did we I think it's the first section. Yeah, I just want to look up the exact equations so you can look that up yourself. And I think the some Fourier in that section, some Fourier transform. Fourier example 20.2.2. The except that that example has the omega is the k, so this k becomes omega, and whatever in front is the a, right? And including the square of 2 pi is the transform formula. Okay, so you can just look up the final answer is 1 over other than c factor c, and square of 2a, a is alpha square t, so 2 alpha square t, exponential, and minus omega square is minus k square, and 4a becomes 4 alpha square t. But that is the after you apply the Fourier transform of Gaussian. That should be the answer in the textbook. C over 2 alpha. Is that alpha or a? Actually, your textbook is a. I write alpha. This doesn't matter. You call it a. Okay, 2t minus k. Well, it's not k. This is the transform. Yeah. This is I'm applying the Fourier transform formula to the inverse transform, so this becomes x. Right? So it's x squared over 4 over 2. Yeah. So that's the final solution. So this is sine uniform, and then you see that for any finite time, finite t, that this becomes a regular function. This is not like a delta function. The delta function is singular, but this is for finite t is not singular. The singularity at t goes 0. At t goes 0 is like taking the limit of a Gaussian and we call for the delta function. Okay, so yeah, no problem. Yeah.
For this case, we can see that k squared x squared.
Yeah. Right.
Same. So how is it transforming to the denominator?
Oh, I've tried the formulas. Yeah. That's what I look. I spent some time looking for that formula because we did that in class. This is one of the examples of Fourier transform. This is, let me write down the equation number. This is by 20.19. Equation 20.19 give you the transform. That example is for transform, Fourier transform. This is inverse transform, so it's just changing the variable. Doesn't matter. Okay. Yeah. Right. Because we are using symmetric, we are using the symmetric convention, so that give you a good conversion. You can convert transform to inverse transform, just interchanging the whether you are using k or x or omega and t. Okay. Okay. So it's about time. Any question? Any more questions? So this is a second example. Hopefully we'll get it done and go to the next section. Yeah. This one. How do I get this one? I'm saying this is by this example. We did that in class. This is example of taking a Fourier transform of a Gaussian, and that involved a DDT, of course, and for that example. But this is an inverse transform integrating dk. But the form is the same. The form of the integration is the same, so I apply the formula. and then find out the corresponding conversion from one set of variable to the another set of variable and write down the solution this way. Just apply this, the solution of this. This is part of the transform formula. This is part of the transform. Okay, yeah, change this. Doesn't matter because the final answer is blue. It doesn't matter. Okay. This is an example. The transform formula we wrote down somewhere, right, at the beginning of section 20.1. The transformer. So did we write it down? The textbook said, just write down transform formula 20.10. 20.10 is a transform formula. And the inverse transform, the textbook wrote it down somewhat later. Yeah. 20.26. That's the inverse transform. Okay. So